Alright, so this is going to be a video about integration using partial fractions. So this is going to be another integration technique that we're going to be covering in this class, and this is going to be used for when you're doing the integration of expressions that you cannot use substitution for, you cannot use integration by parts for, and basically it's when you can actually decompose a rational expression like 1 over x squared minus 1, like I have right here on the screen. We're going to decompose that basically into a bunch of partial fractions. For this course, you only need to worry about linear partial fractions, so that's what we're going to be focusing on, is breaking this down into linear partial fractions. The easiest way to teach this is just through examples, so that's actually what we're going to do. Is I'm just going to show you a couple examples here, so hopefully this stuff makes sense, and you're just, again, following a certain process, following specific technique for this integration. First thing I'm going to do is I'm going to notice I cannot use u sub on this. It wouldn't change anything. It wouldn't make the problem any easier. You would hit a dead end. If you don't believe me, try using u sub. You'll actually see that you run into a dead end with this. Integration by parts wouldn't work as well. So if you want to try that, you can. You'll notice that you hit a dead end. So integration using partial fractions it's usually the biggest sign for this is the fact that you have this rational expression right here that we're going to be doing the antiderivative of. That's kind of the sign that you're going to probably be using partial fractions. First thing we're going to do is we're going to decompose this into two linear partial fractions. So I have this a here. A, we're just going to solve for a later on, but just for right now, just know that it's a variable. And I'm going to break down this a squared minus 1. I'm going to factor it to its linear parts. So I'm going to have x plus 1, and then I'm going to have a capital B, and then I'm going to have x minus 1. Because x plus 1 times x minus 1 is equal to that x squared minus 1. So we're breaking this down into linear partial fractions. That way we can do an antiderivative of it using our old antiderivative rules, the ones that we went over in the previous videos. So we have something like this. We need to figure out what capital A and capital B is, and then we can do these antiderivatives quite easily, because all you're going to be doing is it's basically going to be a over that x plus 1. That's just a times ln of x plus 1 with the absolute value on the x plus 1 plus b times ln of the absolute value of x minus 1. It'll make more sense as we go, but we need to make this so we can actually just do it as 1 over, or in this case a over or b over some other linear fraction, some other linear partial fraction, so that we can actually do the antiderivative. Hopefully as we go through this it'll start making more sense, because right now it's very abstract. First step is decompose whatever that denominator is into its two linear factors. Put a capital A and a capital B. Now there could be multiple capital A, capital B, capital C, that sort of thing, but this one does not have that. The ones that you're going to see on the quizzes in this class aren't going to have that as well. So just focus on capital A and capital B. You might see some practice problems that involve capital C, capital D, other problems like that, but not this one. Okay, so from here, what we need to do is, if we wanted to, and I have seen some people do it this way, is you can solve this to be A times the ln of x plus 1, okay, divided by 1, because the inner derivative is 1, but we don't need to worry about that, divided by 1, plus b times ln of x minus 1 plus c. Now this would be the answer, so we can actually be done with this, but we don't know what that A, that capital A, and that capital B are to be able to solve this problem. So right now that would be our answer, but we need to figure out capital A and capital B. So I'm going to kind of make this more almost algebraic, like an algebra problem, to kind of solve this. So what I'm going to do is ignore all this calculus for a second and just write out that 1 over x squared minus 1 is equal to A over x plus 1 plus b over x minus 1. So I'm not worried about the calculus. I'm not worried about the integration right now. We already know the answer. We just need to figure out the capital A and capital B to finalize that answer. So that's what we're going to solve here with this yellow step. First thing I'm going to do, anytime you see fractions, you are going to multiply both sides by whatever those denominators are to kind of get rid of those fractions. So that's what I'm going to do here. I'm going to multiply both sides by, let's just say, x plus 1 first. You can multiply both of them at the same time if you want. It probably saves a step, but I'm just going to be a teacher and kind of go slower on this. Okay, when I distribute this x plus 1 to this right here, it's basically going to cancel that out. So you're just going to have an a plus, when you multiply it here, you're going to have b times x plus 1 over x minus 1. So we got rid of one of the fractions, which is nice. equal. Now this part right here just factors to our x plus 1 times x minus 1. So what's great about this is this and this will cancel, and now you're left with 1 over x minus 1. Okay, so we're just breaking down all of those fractions to make it so we don't have them anymore. We don't want fractions. The easiest way to get rid of a fraction is by multiplying by those denominators. We're going to keep doing this. We're going to multiply by the next denominator on both sides. So what I'm going to do is multiply all of this by this denominator, x minus 1. I'm going to do this to both sides. What you do to one side, you equally have to do to the other. And when we distribute this over here, you're going to get a times x minus 1 plus, now this one's going to cancel, so you're just going to have b times x plus 1. This and this are going to cancel, so you just end up with 1. So if you notice, that last equation now looks very pretty compared to where we started. We have no more fractions. It's a lot easier to work with. So we just basically need to solve this equation for a and b, and we're good to go. So first thing I'm going to do is just to make my life a little bit easier. This equation is always true for any x, so I'm just going to make the x equal to 1, because if x is equal to 1, this whole thing becomes 0, which means the whole thing is gone. So that's the goal here. So for x equals 1, you're going to end up with 1 is equal to 0 plus b times 1 plus 1. Okay, well that's just 2b. What's great about this is now we just solved for b. b is equal to 1/2. Okay. Now we're going to do the exact same thing, only this time we're going to have x equals -1, because then this part right here is going to be equal to 0. So now you're going to have 1 is equal to a times -1 minus 1, because this x right here is just going to be -1 minus that 1. And it's going to be 1 is equal to -2a, which means a is equal to -1/2. The whole goal of this was to figure out what our a is and what our b is. That way we can finish out this problem up here with this orange step right here. Okay, remember the orange step was our answer, but we need to figure out what capital A and capital B are. Well, we just did that. So now what we can do is we can kind of finalize this a little bit and say that this is equal to -1/2 ln of x plus 1 plus 1/2 ln of x minus 1, and then you still have the plus c. Now, if you remember from your previous math classes where we covered log rules, you can actually simplify this out. You can basically factor out that 1/2. So I'm going to do that now. And because this one's minus in front, if you remember with logs, you can actually subtract them out. Actually, I'll write down the property for logs that I'm talking about. So if you have the log of something, let's just say it's a, minus the log of something else, let's just say it's b, it's actually equal to the ln of a over b. So I'm going to use this formula essentially on this light purple step here. It's minus here, so this one's going to be on the bottom. If you notice, whatever's after the minus is on the bottom, the b. So I'm going to use that to basically simplify this answer a little bit more. All right, so we're going to factor out that 1/2 because there's a 1/2 in both of them. And then you're going to have ln of the -1 goes on the bottom. The one that's the minus goes on the bottom. So that's x plus 1. Top is going to be x minus 1. You have to do the absolute value for this. You still have to have that plus c as well. So using log properties, it would simplify to something like this, and that's the final answer. The things I want you to realize on this is a lot of steps. We're going to have to practice this a lot. Lots of steps, lots to work around, lots of algebra actually too. Lots of color changes. Make sure you understand what I did for each of them. The main thing, that first red step that we see there, is you have to break it down into linear partial fractions by factoring that denominator right away. Then you can simplify it out just using logs, just using the antiderivative of 1 over x is ln of x, absolute value of x, plus c. And you simplify it out, that a over x plus 1 as a times the ln of the absolute value of x plus 1. You do the same thing with that b over x minus 1, but then you have to figure out what that a and that b are. That's what I did in the bottom left corner there, just to kind of make sense of all of that. Let's do another example problem just to kind of consolidate this a little bit more. I'll give you one that's a little bit different than the one we just did, just to kind of shake it up a little bit, because you need to be able to do multiple types of these problems. All right, so this next problem is as follows. All right, for this one, it's already factored on the bottom, and that usually tells you a pretty big hint that like you're probably gonna have to use linear partial fractions on this. So that's the first thing that we're gonna be using on this, is the fact that you have that already factored on the bottom. All right, so I'm gonna rewrite this. So this is gonna be equal to the integral of, put a parentheses here, a over one of those linear partial fractions plus b over the other linear partial fraction dx. And I shouldn't say linear partial fraction, I just say that linear expression there, but you understand what I'm trying to say here. All right, now from here, you could easily solve this without, I mean, you have to calculate the a and the b later on, but we can easily solve this just as is. It's just going to be a times ln of 2x minus 3. Now, there is an inner derivative here of 2, so you are going to have to divide this by 2, because the slope there, that inner derivative is 2. You could just think of it this way. If you had to do the derivative, you'd be multiplying by that inner derivative of 2, so it has to kind of cancel out. So divided by 2 will cancel that out. We didn't have to do that before because we just had like the linear equation, the slope was 1. Like for example, the slope here is 1. Well, dividing by 1 just gets you the same thing. So we have to divide by 2. If you want, you could also do integration by substitution on this, and you'll see that it's a divided by 2. But the easiest shortcut is when you have this linear thing here, whenever that's linear, just divide by whatever the slope is once you do the antiderivative. It just makes your life a lot easier. Plus b times the ln of x plus 2. We do not have to divide by 1. If you want to write it down in there, that's fine. You can divide by 1, but you don't need that. And then we're going to have a plus c. So if you notice again, we're in the same predicament that we were in last time. We need to figure out what that capital A and capital B are so we can actually finalize this answer. So that's what we're going to do now. Going back to algebra mode, we know that 7x divided by 2x minus 3 times x plus 2 is equal to the decomposition of these linear partial fractions. Something like that. Again, no derivatives, no antiderivatives on this, just straight up algebra. What I'm going to do is I'm going to multiply. This time I'm going to multiply by both factors right away. So I'm going to multiply both sides by 2x minus 3, and I'm going to multiply both sides by x plus 2. You can do this right away. You'll notice it does save a little bit of time just to do it all in one foul swoop. But if you want, you can just do it one by one. You're going to get the same answer either way. It just takes a little bit longer to do. Now, what's great about this is going to cancel with this, and this is going to cancel with this. So then you end up with 7x is equal to, when you distribute all this to this first part right here with the a, the 2x minus 3 is going to cancel, and you're just going to be left with a times x plus 2. Plus, now you distribute here, the x plus 2 is going to cancel with that other x plus 2, and then you still have b times 2x minus 3. Okay. So these both are going to cancel with those, and you end up with something like that. Okay. Again, this one is still going to have that 2x minus 3, which I wrote below. This one's still going to have that x plus 2, so I'll just write that in there for fun. All right, now from here, we're going to be solving for a and b again. The easiest way to do that is to pick values of x, in which this will be easier to work out. So first thing I'm going to do is just x equals -2, because this part right here is going to be equal to 0, so it makes the solving pretty easy. So it's going to be -14, because it's going to be 7 times -2 here, because the x is -2, is equal to 0. You don't have to write the 0 in, I'm just doing it for fun, times b times 2 times -2 minus 3. Okay, if we simplify this out, it's going to be -14 is equal to -7 times b, because this right here is equal to -7. This is going to yield us b equal to 2. Okay, so now we solve for b. Now we're going to do the exact same thing, only for the a. So let's do this equal to 0. That means x is going to be equal to 3/2 this time. So now we're going to put 3/2 in for all the x's. So you're going to have 21 over 2, because when you do 7 times 3 halves, it's 21 over 2. And that's going to be equal to a times 3 halves plus 2 plus 0. Okay, from here I'm going to simplify everything. So this is going to be 21 over 2 is equal to a times, okay, this is going to be 4 over 2 here because 2 is equal to 4 over 2. I just need common denominators. So it's going to be 7 over 2 here. I'm going to multiply both sides by 2, divide both sides by 7, and your a should be equal to 3. Okay, so b is 2, a is 3. We can go back to that orange part right here and finish out this problem now. A was 3, so it's going to be 3 halves ln of 2x minus 3 plus 2 ln of x plus 2 plus c. All right, and that's the answer. So that's a video on the integration using partial fractions. I did linear partial fractions. That's all you're going to be expected to understand for this class. We're not going to do anything with like quadratic partial fractions or anything like that. Make sure you follow the steps. This stuff is very, very, very difficult. If you haven't noticed yet, the other two integration techniques that we've covered so far were also very difficult. You are going to want to practice this. If you're taking this class in the summer, it's only an 8-week course, so you do not have a lot of time to really understand this stuff. So you have to be really, really on top of this stuff. Make sure you ask questions if you got them. You can email me or put a comment in this video. I know this is complicated, but if with enough practice, you should be able to do it. So if you have any questions about anything in this video, let me know.